So by using these proxies to reconstruct paleoclimates, we know not the exact temperature, but to a pretty good degree, at least whether it was relatively warmer or relatively colder, and we can estimate what the temperature was um, of Earth's history thousands to millions to billions of years ago. And what we see is, if you look at the bottom part of this graph where it shows the stages of glaciation over the past 1,000 years or so, we can see that, yeah, there appears to be a cycle of it gets really hot and then it gets really cold, and it gets really hot and it gets really cold. It gets really hot, it gets really cold, right? There's this natural cycle of climate change. That means that the global warming that we are seeing today is not necessarily a completely unique event. There are some things unique about it, which we'll talk about later. Right? But Earth has been really, really hot before. It's been much, much hotter today in the past, right? And that's been natural. And by looking at these periods of hot and then cold and hot and then cold, right, we see that there are some patterns. It's not just chaotic, sometimes hot, sometimes cold with no, rhyme or reason. There are some cycles that we can pull out. And we're able to see that those cycles are caused by external forces, meaning forces that are outside of humans, right, that are just happening to Earth naturally. The first thing we can see is orbital forcing, and that means the Earth changing temperature due to the way that celestial bodies, so the sun, the Earth, Jupiter, Saturn, right, orbit around each other and influence each other's orbits. So we call these Milankovitch cycles. The Milankovitch cycles include 3 different types of orbital forcings. We've got precession, which has a frequency of about every 20,000 years. Obliquity, which has a frequency of about 40,000 years. And then eccentricity, which has a few different cycles, but on average, we say that it's about 100,000 years or so. Right? Now, what each of these are, is, again, it's the way that Earth orbits the sun. So eccentricity deals with the shape of the Earth's orbit around the sun. The Earth's orbit around the sun is nearly circular, but it's not a perfect circle. And sometimes it gets a little what we call eccentric, meaning a little bit ovoid. The picture here is really, really exaggerating that elliptical orbit just to show you what I'm talking about. It's most of the time it's very near circular, but it gets a little less circular sometimes. And there's that periodicity to that. It's about every 100,000 years, the Earth goes from more circular to more elliptical, more eccentric. And notice that when the orbit is highly eccentric, right, more like an oval, the Earth is closer to the sun for a longer period of time as it's orbiting around the sun over a single year. That means that summers actually grow longer when Earth's orbit is elliptical. And overall, that increases Earth's yearly average temperature. So when the orbit is highly eccentric, Earth gets hotter. When Earth's orbit is nearly circular, Earth gets colder. Right now, we are in a nearly circular orbit, and we are getting more circular, which means that eccentricity alone would cause Earth to be cold and cooling. Right? The next one we're going to talk about is obliquity. Obliquity is Earth's axis tilt, right? We know that the tilt of Earth, or that Earth is tilted, right? That's why we have seasons. That's why, right, the north part of, or the northern hemisphere and the southern hemisphere experience different seasons because one of us is always tilted away from the sun, whereas one of us is always tilted towards the sun. But the tilt of that axis varies over time. Not hugely, right? Earth's not flopping over, but it does vary by a few degrees over time. And when that tilt is greater, the difference between the seasons is greater. So summers are hotter, winters are colder, right? And when that tilt is less, the seasons get closer to each other. So you can imagine that in order to go into, say, an ice age, you would need to have very extreme winters. You would also need for those summers to not completely melt the ice. So if you have a really extreme summer, you might not be able to go into an ice age. All right. The next one is the precession. And I think of precession kind of like, like when you spin a top and at first it spins really, really nicely, but then near the end of its spin, it starts to wobble. That's precession. It's like the wobbling of Earth. And again, this just impacts, right, the seasons, and it impacts on a yearly average how much solar radiation is coming to Earth. And when you add all three of these Milankovitch cycles together, that explains a ton of this cycle of Earth's hot and cold cycles, right? But it doesn't explain all of Earth's hot and cold cycles, right? Notice there are a few, little blips in there that don't seem to be explained by the Milankovitch cycles. Those other little blips in there can be explained by two other things, two other external forces: solar forcing and volcanic forcing. So the sun is, right, not just a constant ball of fire, it's constantly changing. There's sometimes more sunspots, sometimes fewer sunspots, sometimes more solar flares, sometimes less solar flares. Like, it's a dynamic object. And so sometimes it's just sending out slightly more solar radiation, sometimes it's sending out slightly less solar radiation, and that's going to impact Earth's climate. We also know of volcanic forcing, right? So volcanoes are actually super interesting. When they erupt, first, when they erupt, they're going to send out a lot of stuff into Earth's atmosphere, but two big components are greenhouse gases like carbon dioxide and methane, but also they're sending out a lot of aerosols, right? A lot of ash, a lot of dust, a lot of water vapor, things like that. And so the aerosols are what are going to have the first impact. The aerosols, as we know, hang out in the atmosphere for a few years, and they block the incoming solar radiation. It's kind of like putting up an umbrella, right? It's shading the Earth, it's cooling the Earth down. But those aerosols do eventually fall out, and that ash will eventually deposit to Earth. And then all that's left in the atmosphere are those greenhouse gases, right? So because of the aerosols, first, after a volcanic eruption, Earth's climate cools. But then after 2 years or so, when those aerosols are gone, Earth's climate then warms because the greenhouse gases become the only component of what's left in the atmosphere. Right? So we see that after these huge volcanic eruptions, we do see extreme cold and then extreme hot. And especially, and I'm not just talking about, just one volcanic eruption that has this huge impact on Earth's climate. I'm talking about cycles in Earth's tectonic history where all around the world, sometimes tectonic activity was just very extreme, and we had a lot of large volcanoes going off all at once, all around the world, and that caused Earth to go into a very, very hot period for a long period of time. All right, so when you put all these external forces together, the orbital forcing, the solar forcing, the volcanic forcing, we can explain the vast majority of the hot and cold climate cycles we've seen in the past. Okay? And by doing this, we can also see that the amount of greenhouse gases in our atmosphere, particularly carbon dioxide, play a huge role in the amount of ice that's present on Earth. Okay? And again, we can estimate the amount of ice present by looking at ocean chemistry. So, right, looking at this plot over the past 450,000 years, if you plot the amount of carbon dioxide in our atmosphere and you plot the amount of ice on Earth, you see it's almost a perfect match, right? Very obviously, the amount of carbon dioxide is going to influence the amount of ice. The more carbon dioxide you have, the less ice you have, right? And by looking at these really long records over hundreds of thousands to millions of years, we can see that present-day climate change cannot be explained by natural variability, right? As I said, Earth's eccentricity, which is the largest cycle of the largest component of the Milankovitch cycles, according to eccentricity, we should actually be cold and getting colder right now. Right? We also haven't had any huge, volcanic eruptions or any extreme tectonic events recently. Like, there's none of these external variables that we can look at and say, yeah, that's causing climate change, right? No, what we're seeing now is not caused by an external forcing. Instead, we know that present-day concentrations of these greenhouse gases exceed the range of concentrations recorded in ice cores during the past 800,000 years, right? That's a really long time. We also know that the current rate of increase of these greenhouse gases and the associated radiative forcing are unprecedented over the past 22,000 years. Now, I'm not saying that before this, the rate was normal. I'm just saying that we can only say to the past 22,000 years because that's the only time when we have high resolution ice core data. The older the ice layers, the more squished they get, the lower the resolution is, right? But, right, we know that one, what we're seeing today is not naturally caused by external forcing because, right, we can look at graphs and very easily explain all of the other climate events on Earth by external forcing until today. And the external forcings just don't make sense anymore in terms of the climate we're seeing. And we know that the amount of greenhouse gases in our atmosphere are unprecedented over the past almost 1,000,000 years. And that the rate of increase is also unprecedented, at least in the recent geologic past. So something else has to be causing this.